Hello friends, welcome to this lecture. In this lecture we continue our study of boundary value problems, and in this lecture we will discuss the very special kind of boundary value problem, that is Sturm-Liouville boundary value problem. So let us first define what is a Sturm-Liouville boundary value problem. So first we discuss the differential equation of the form py dash dash plus qy plus lambda ry equal to 0 here. So here this is a by looking you can say that this is the self adjoint differential equation. Here p dash q and r are real valued continuous function on closed interval a and b, and lambda is a real parameter. And also let us assume that this px is never 0 in this interval. So without loss of generality, let us assume that px is greater than 0, and also we assume that the coefficient of y function, that rx, is also greater than 0. So this is known as Sturm-Liouville equation. A Sturm-Liouville equation without putting this condition that px and rx are non-negative. So here we simply consider this equation given as equation number 12. We say that it is a self adjoint equation and given in this form, and we call this as Sturm-Liouville equation, and with the condition that p dash q and r are real valued continuous function. And here we consider the boundary conditions. So Sturm-Liouville equation along with boundary condition, and then it is known as Sturm-Liouville boundary value problem. So boundary conditions are given either in this form or this form. So here the first set of boundary condition is this, that m1 y of a plus m2 y dash a equal to 0, and m3 y of a plus m4 y dash a equal to 0 here. So here boundary condition is given in 13a and 13b. So here if you look at the one condition is given at the point x equal to a, t equal to a, and the other boundary condition given in at the point of b. So here we have m1 y of a plus m2 y dash a equal to 0, and m3 y of b plus m4 y dash b is equal to 0. So these kind of boundary conditions are known as separated boundary conditions, because they are separately defined at point a and b. And there is one more kind of boundary condition, that is periodic boundary condition, that is y of a equal to y of b and y dash a equal to y dash b. And if we are considering one more condition, that is p of a equal to p of b. So we call these kind of conditions as periodic boundary conditions. So initial whatever be the value at the initial point, that is the value given at the end point. So it means that y of a equal to y of b, y dash a equal to y dash b, and so on. So and here we are assuming that in 13 one of the variable m1 m2 must be non-zero. Similarly one of the coefficient, that is m3 m4, are non-zero constants. So here we assume that m1 square plus m2 square is non-zero. Similarly m3 square plus m4 square is non-zero. So at least we are saying that these are not trivial boundary conditions. So a boundary value problem consisting of equation number 12, that is Sturm-Liouville equation, along with boundary condition whether it is 13a or this 14. This we say that this system is called regular Sturm-Liouville boundary value problem. Here regular means what? First of all, we define what is Sturm-Liouville boundary value problem. So for defining Sturm-Liouville boundary value problem, we consider Sturm-Liouville equation, that is SL equation, and one of the boundary condition, either it is 13a or 14. Then we call this as Sturm-Liouville boundary value problem, and then we define a regular Sturm-Liouville boundary value problem. It means that our problem is regular in the sense that your the point a, b, these are finite endpoint, that none of a and b are infinite, and the coefficient of highest order derivative, that is y double dash, that is p here, is non-zero in this interval. If it is happening, then we call this SL boundary value problem as regular Sturm-Liouville boundary value problem. Okay. So here we say that we already know that since it is a homogeneous equation, so trivial solution is always exists. So it means that ideally 0 function on AB is always a solution of Sturm-Liouville problem, and we say that this solution is a trivial solution of this boundary value problem. But we are more interested in finding the non-trivial solution. So we say that for a value of this parameter lambda, let us say that y lambda is a non-trivial solution of 12 with 13a 13b or 12 with 14. Then this parameter, the value of this parameter for which we have a non-trivial solution, the value is known as eigenvalue and the corresponding solution is known as eigenfunction. So our idea of considering the Sturm-Liouville boundary value problem is to find out the parameter lambda for which this has a non-trivial solutions, and we see that this has a very useful application, and in fact we say that the application, one very important application is that this system has a complete orthonormal system of eigenfunctions, and we used these eigenfunction in expanding a certain class of function that we see as an application of Sturm-Liouville boundary value problem. And you can see that some very important boundary value Sturm-Liouville boundary value problems are the examples of Legendre polynomials and Bessel's polynomial, and we have already seen that how a given function can be written as expansion of Legendre polynomials or Bessel's polynomials. So here we see the general theory behind this. So here idea is that throughout this lecture we always try to find out the value of the parameter for which we have a non-trivial solution, and the set of all eigenvalues of a regular problem is called its spectrum. So set of all eigenvalues is known as spectrum. So now let us consider one example of finding all the eigenvalues and eigenfunction of the boundary value problem. So if you look at y double dash plus lambda y equal to 0. So first let us see that this equation is given in terms of self-adjoint form. So here coefficient of y double dash is 1 and coefficient of y dash is simply 0. So we can say that this equation is given in self-adjoint form. Now we have a boundary condition. Boundary condition is given as y0 is equal to 0 and y pi equal to 0. So these boundary conditions are separated boundary conditions. So it means that this system of boundary value problem is a regular regular Sturm-Liouville boundary value problem, because here endpoints are also finite and coefficient of y double dash is non-zero. So we say that this system is a regular Sturm-Liouville boundary value problem, and we want to find out the parameter lambda for which we have a non-trivial solution, for which let us consider several cases. So since lambda is a real number, so it can take either a 0 value, positive value or negative value. So we will consider one by one. So first let us consider the simplest case, that is lambda equal to 0, and in this case our equation reduced to y double dash is equal to 0, and we already know that the solution is simply a linear solution. So it means that y of x equal to a of t plus bt, at plus b, and we can find out the coefficient a and b, sorry it is y of t not y. So you can find out the coefficient a and b by this y of 0 equal to 0 and y of pi equal to 0, and you can simply say that since y 0 equal to 0, this implies that b is equal to 0. Now y pi equal to 0 means you can say that we have that a equal to 0. So in case when lambda is equal to 0, then we have only a 0 solution, that is yt is equal to 0 is the only solution, and we say that we do not have a non-trivial solution. So this is not very useful to us, and we simply say that lambda equal to 0 is not an eigenvalue, because eigenvalue we say when we have a non-trivial solution corresponding to the value of the parameter. So we say that lambda equal to 0 is not an eigenvalue of equation number 15. So now let us consider the next case, that is lambda less than 0. So when lambda is less than 0, we can write it lambda as minus of mu square, where mu is some real number, and we say that solving this we have this equation y double dash minus mu square y equal to 0, and we already know the solution of this. Solution of this is basically what, let me write it, y double dash minus mu square y equal to 0. So we can write it solution of yt is equal to e to power mu t let me write it a plus b e to the power minus mu of t, and we need to find out the coefficient a and b. For that, let us utilize this condition y0 equal to 0 and y of pi is equal to 0. When you apply y0 equal to 0, then it is a plus b equal to 0, and when you apply y pi equal to 0, that is a to the power pi t plus b e to the power minus pi of t is equal to 0. And when you simplify this, that is 1 1 e to the power pi t and e to the power minus pi t, and here we have a b is equal to 0 0, and you can simply say that the determinant of this coefficient matrix is non-zero. So it means that this is invertible, and you can say that your solution is only that a equal to 0 equal to b. So it means that here we have only a trivial solution because your a and b are 0. So we have only a trivial solution. So we say that we does not have any non-trivial solution. So lambda less than 0 is also not the eigenvalue. So it means that any lambda for which any non-negative value of lambda is also not an eigenvalue of 15. So now let us move to next condition, that is lambda greater than 0. So for that let us assume that lambda equal to mu square, where mu is any real number, and hence we can write it our equation as y double dash plus mu square y equal to 0, and we already know that solution is yt equal to c1 cos of mu t plus c2 sin of mu t, and we need to find out this c1 and c2. For that, y0 equal to 0 equal to y of pi. When you put y of 0 equal to 0, so the 0 equal to here we have c1 because so c1 is coming out to be 0. Now y pi equal to 0, when we put y pi equal to 0, we have 0 equal to c2 sin of mu pi. So it means that we have c2 sin mu pi. Now we already know that if c2 is 0, then we have only a trivial solution, which is not useful to us. So let us find out the values of mu such that this c2 sin mu pi has to be 0. So we say that if mu of pi is n pi, where n is 0 1 2 3 and so on, then we simply say that we have a non-trivial solution. Then in that case we can choose any value of c2. So here we can say that when lambda is greater than 0, then we can write lambda equal to mu square as we have pointed out, and solution is given as yt equal to c naught cos of mu t plus c1 sin of mu t, and when you use y0 equal to 0, we know that c naught equal to 0, and y pi equal to 0 implies that c1 sin mu pi equal to 0, and we have a non-trivial solution only when mu pi is equal to n pi, where n is any integer value. So it means that calling that mu n as n, we say that for each n equal to each n belonging to z, we have a solution, that is sin of n t, right. And in this case we say that our lambda n, which is mu square, that is n square, is the eigenvalue. So n square is the eigenvalue, and the corresponding solution is sin of n t. So here your eigenvalues are what? Eigenvalues are every integer value is an eigenvalue, and this corresponding eigenfunction is given as sin of n t. So here we are able to find out eigenvalues and eigenfunction of a given Sturm-Liouville boundary value problem, that is this here. So now proceed further, and we have this very important result, which says that assume that a and b are finite real numbers. So we have a finite endpoint, and the functions p dash t, q t and r t are real valued continuous function on this closed interval a b, and that m1 m2 m3 and m4, that is the coefficient present in boundary conditions, are real numbers. Then the Sturm-Liouville problem 12 with 13a 13b or 12 with 14. Now 12 is what? Sturm-Liouville equation, and 13a 13b are separated boundary condition, and 14 is the periodic boundary condition. So we say that if a, b and c satisfy, then we have countably many eigenvalues with no finite limit point. Corresponding to each eigenvalue we have eigenfunctions. So this is the existence theorem of eigenfunction. Here I am not going to prove this, we assume the statement and the result of this theorem as a result which gives us license to work with eigenvalues and eigenfunctions. So, without providing the proof of this, we are using this theorem as a existence theorem for eigenvalues and eigenfunctions, and we say that eigenvalues are countably many, and corresponding to each eigenvalues we have eigenfunctions. Here we have eigenvalues are like discrete eigenvalues, and we say that discrete eigenvalues means these are not continuous spectrum, it is only discrete one. Okay. So, all this we have utilized. So, it means that in regular Sturm-Liouville boundary value problem we have this theorem to provide the existence of eigenvalues and eigenfunction. Now, once we have existence of eigenvalues and eigenfunction, then we start working with these eigenvalues and eigenfunctions. So, next very important result is in the direction of orthogonal eigenfunctions. So, before that, what do you mean by orthogonal function? Let us define it. So, two distinct function x and y define and continuous on this closed interval a b are said to be orthogonal with respect to a continuous weight function r t if a to b r s x s y s d s is equal to 0. So, here when this condition holds, then we call this as that x and y are orthogonal to each other with respect to the weight function r of s, and this is very important property which is preserved by if you look at Legendre polynomials, Bessel's polynomials, and many more spatial function which is nothing but a byproduct of this Sturm-Liouville boundary value problem. So, this is very important property, and it says that these regular Sturm-Liouville boundary value problems consist a complete orthogonal system of eigenfunctions. So, let us that we are going to discuss in next class. Now, let us discuss next theorem. Say let all the assumptions a and b of theorem 15, theorem 15 is existence of eigenfunctions hold, and for the parameters lambda and mu, where lambda is not equal to mu, let x and y be the corresponding solution of 12 such that this value, that is p Wronskian of x y given at b and a is equal to 0. Basically it is what? It is p w x y given at a given at b minus, or you can equal to p w x y given at a are same. So, this quantity is same, then we say that a to b r of s, x of s, y of s, ds equal to 0. So, we say that if this condition hold, what are conditions? Condition is that a and b are finite real numbers and the function p dash t, q t and r t are real valued continuous function, then the Sturm-Liouville boundary value problem has orthogonal solution corresponding to distinct eigenvalues. So, it means that when lambda and mu are not equal, then corresponding to lambda, let us say x is the solution of the Sturm-Liouville boundary value problem, and corresponding to mu we have y as a solution of the boundary value problem, then x and y are orthogonal to each other with respect to the weight function r of s. So, let us prove this, and this is true when we have the following condition, that is this. So, let us prove this. So, from the hypothesis of the theorem we know that corresponding to lambda, x is the solution of this Sturm-Liouville equation. So, p x dash plus q x plus lambda r x equal to 0 and p y dash whole dash plus q y plus mu r y equal to 0. So, that is what is given here, that x is a solution of this and y is a solution of this. So, it satisfies this. Now, simplify this by multiplying the first equation by y and multiply the second equation by x and just subtract it. So, here when you multiply, what you will get, this term will be cancelled out, q x y minus q y x, it is gone. So, here in let me write it here. So, it is what, p x dash y plus q x y plus lambda r x y equal to 0, and here we have p y dash x plus q x y plus mu r x y equal to 0. When you subtract it, these term will simply gone, and we have lambda minus mu rxy. So we have lambda minus mu rxy equal to py dash whole dash x minus px dash dash y. So we have this thing. Now we can simplify and we can write it lambda minus mu rxy equal to d by dt of py dash x minus px dash y. Here we simply add this term py dash x dash, and we can write it like this. In fact, you can easily check that if we expand it, we will get this only. So here we have done this py dash dash x plus py dash x dash minus py dash x dash minus px dash whole dash y, and if you simplify, you have this thing, that d by dt of py dash x minus px dash y. So then we integrate this with respect to with respect to t from a to b. So when you integrate this last equation 17, we have lambda minus mu a to b r of s, x of s, y of s ds equal to, now here this derivative will go out, and we have py dash x minus px dash y evaluated at b minus a. So now look at this equation is already given. What is given here, that p Wronskian of x y at a to b is equal to 0, means what, p, now Wronskian of x y is x y dash minus x dash y given at b is equal to 0. So this is already given, so which is written here, p x dash y b at a. So here we can say that this quantity is going to be 0, because that is given as an assumption here. This is the condition we have given. So it means that this right hand side is simply gone. So we have lambda minus mu into a to b rs xs ys ds equal to 0. Now lambda is not equal to mu, that we have already assumed. So it means that from the assumption we have that this quantity has to be 0. That is what we wanted to prove, that the solution corresponding to different distinct eigenvalues are orthogonal to each other. That is what we wanted to prove. Now next we want to show that we have already proved that if certain condition hold, that is p of Wronskian of x y at b is equal to p w x y at a, if these two are equal, then distinct eigenfunction corresponding to distinct eigenvalues are orthogonal to each other. Now see that how this boundary condition which we have assumed, that is separated boundary condition and periodic boundary condition, are helpful to find out that this condition is trivially hold. So for that, let us consider this following theorem. Then let the hypothesis of theorem 15, that is the existence of eigenfunctions theorems, be satisfied, and let xm and xn be two eigenfunction of the boundary value problem corresponding to two distinct values lambda and m and lambda n, then this boundary condition holds true. Because if you look at we have assumed that if this boundary condition hold, then the corresponding eigenfunction, that is xm and xn, are orthogonal to each other with the weight function r of x. Now we want to show that if we have a boundary condition, that is 13a 13b is true, then this condition is automatically true. Now here in addition to this, if we say that if pa is equal to 0, then this condition holds without use of 13b, right, 13a, and if pb is equal to 0, then this equation holds with the 13b being deleted. So it means that if pa equal to 0, then we have to use only one condition. If pb is equal to 0, then we can use only one condition. So without loss of generality, let us assume that we none of this pa and pb is 0. So let us assume that pa is not equal to 0 and pb not equal to 0. In fact, let me write it here. This is what, this is pb Wronskian of xm xn given at b minus p of a Wronskian of xm xn at a is equal to 0. Now if pb is 0, then I need not to use this, only this is sufficient. That is what it is written here. Then if pb is equal to 0, then we have to use only one, that is 13a, and if pa is equal to 0, then we have to use only one condition, that is 13b, and the boundary condition given at the point x equal to t equal to b. So, let us assume that none of this P A and P B is 0. So, from this theorem we have that since x n and x m both are solution of this. So, let us write it m 1 that they must satisfy the boundary condition, that is m 1 x n a plus m 2 x n dash a equal to 0, and similarly x m will also satisfy the boundary condition, that is m 1 x m a plus m 2 x m dash a equal to 0. So, here let us assume that this m 1 is not equal to 0, because if m 1 is equal to 0, then this is quite easy. We will see what is going to be easy, because if m 1 is not equal to 0, then we can simplify this these two equation by eliminating this m 2. So, here you can eliminate m 2 from these two equations, and we can write our equation as m 1 x n a x m dash a minus x m a x n dash a equal to 0. So, here we are assuming that m 1 is not equal to 0. If m 1 equal to 0, then this is very easily we can obtain like this, but now coefficient is going to be m 2. Now, we have this. So, since m 1 is not equal to 0, so we can cancel it out, and we have this thing that x n a x m dash a minus x m a x n dash a equal to 0. So, this we have obtained from 13a, that is the boundary condition given at the point x, t equal to a. Similarly, if we assume that use 13b, that is let us assume that m 3 is not equal to 0, then in a similar manner we can prove that x n b x m dash b minus x m b x n dash b is equal to 0, and we can easily see that if P A equal to 0, then this 19 is not useful, and if P B equal to 0, then this is not useful, and we can say that from equation number 8, let us simplify this P W x m x n given at b at a is equal to P B x n b x m dash b minus x m b x n dash b. Now, since P A equal to 0, so we are not looking at the condition given at x t equal to a. So, we have this. Now, if you look at the in a bracket, whatever is here is trivially 0, because we have already proved it equation number 12. So, it means that boundary condition 13b implies that 20 is true. Now, 20 is true means this Wronskian this P W x m x n given at b and a is equal to 0 if P A equal to 0. Similarly, we can handle the case then P B equal to 0. So, it means that if P A and P B both are non-zero, then we can simply say that this is what this is written as P B, and this is x n b x n b x m dash b minus x m b x n dash b minus P of a x n a x m dash a minus x m a x m dash a. So, we have from 19 this is 0, from 20 this is 0. So, it means that this quantity is going to be true. So, we have seen that the condition, this condition, that is P W x m x n at a and b is equal to 0 is true when we assume the condition that 13a and 13b, that is the separated boundary condition, if we use, then this is automatically true. So, now we look at the other case, and consider that hypothesis of theorem 15 be satisfied, and let x m and x n are eigen functions of the boundary value problem 12, and 14, that is periodic boundary conditions are true corresponding to distinct eigenvalues lambda m and lambda n, then x m and x n are orthogonal with respect to the weight function R T. In fact, only thing we have to show is that this quantity, this is going to be 0 here. So, let us look at here, we since we have this P W x m x n, b at a is can be expanded in this form P B into the Wronskian of x m x n, that is x n b x m dash b minus x n dash b x m b minus P of a x n a x m dash a plus x n dash a plus x m a. Now, here we simply say that if we use the periodic boundary condition, then we can make this quantity 0. So, here we use x n b is equal to x n a. xm dash b is equal to xm dash a, xn dash b is equal to xn dash a, xn b is equal to xn a, and we have also assumed that p of b is equal to p of a. So we can say that here this periodicity condition, if you apply, then this quantity is equal to 0. So it means that if this quantity is 0, we have already proved that if this condition is true, then a to b are s xn s xm s d of s is equal to 0 here. So in case of periodic boundary condition, that is Pb equal to Pa, x a equal to xb and x dash a equal to x dash b, this quantity is 0, and hence your xn and xm are orthogonal to each other with respect to the weight function r of s. And previous theorem says that if we have the separated boundary condition, then this is automatically true. Here we need not to assume that Pa equal to Pb, but when we consider the case of periodic boundary condition, then we have to consider the function Px also. So here we have discussed some important properties of eigenfunctions. What we have discussed is that we are considering the regular Sturm-Liouville boundary value problem, and we have seen that eigenfunctions, existence of eigenfunction, that is theorem 15 we have discussed. And not only this, we have discussed that in the case of separated boundary condition or periodic boundary condition, the regular Sturm-Liouville boundary value problem has a orthogonal set of eigenfunction corresponding to distinct eigenvalues. So, and in next class we will see some more properties of eigenfunction and eigenvalues and the use of eigenfunctions in many other field. So with this I am just summarizing my lecture, and we will continue in next lecture. Thank you very much for listening. Thank you.